Hey everyone, I'm Hugo, a second-year PhD student in the EP2 group and under the supervision of Mario Merino. And my PhD is about the study of plasma wave interaction in electron-less plasma thrusters and its optimization. For this talk, we can already actually skip the last part of the title. And I would like to introduce in more details actually what this is about, starting with electron-less plasma thrusters. So far in our presentation of our group, you saw mostly plasma thrusters that work with electrodes, but EPTs, as their name suggests, they don't have any, as the plasma is, the power is coupled to the plasma via electromagnetic fields. So this brings some advantages that has been already stated before by Andres quickly, as durability or flexibility with propellants. The two main kinds of EPTs are first the helicon plasma thruster, so that you just saw with Andres. But the main one that will be the focus here is the electron cyclotron resonance thruster, or ECRT, that relies on microwaves and on the ECR phenomenon for power absorption in the plasma. So here is a sketch of the axisymmetric domain of the thruster. On the left, you have the waveguide that brings the waves towards the plasma chamber in the middle, which is the main region of interest in this case, because this is where you have the ECR line. For the first part of the title of the thesis, the plasma wave interaction, so as we saw about EPTs, if we want to optimize their performance, we need to optimize the power coupling that takes place in the plasma wave interaction. So to study this, we use numerical simulations that allows us to run different tests and iterate over different operational parameters. To do that, we need a code to model the plasma transport. So we will use hyphen, that has been also presented by Iñaki and Simone, that will take care of the plasma. And we need to couple it with a code modeling the wave propagation and its interaction with the plasma. For this, we'll use the wave module, and that will take the plasma density maps from hyphen and compute the corresponding power deposition. And then this power deposition is sent back to hyphen, and this closes the loop of the simulation. So in this work, we will focus only for now on the wave module, which is a finite element code that relies on the cold plasma model. So the cold plasma model is a simple model that encapsulates the response of plasma to the waves through the electric tensor kappa in the wave equation. The dispersion relation that you get from the wave equation gives you the resonances and the cutoffs of the waves that themselves, they define different regimes of wave propagation that can be represented in the CMA diagram as different regions. So here I highlighted the main ones. So you have the regions 3, 7, and 8, for example, that are regions of interest in this work because they are regions with resonance cones. And so we will keep region 8 for this study as a reference for this, and we'll compare it to region 1 as a general reference case for low density plasmas. So for the physical part of it, we then have the cold plasma model, and for the numerical part, we will use, as I said, the finite element method with a mixed element formulation. So now we can run wave simulations into the ECRT domain I presented before. So here we will show the results in the discharge chamber. And these are the first results we have. So here you have the three components of the electric field. And what we can see is that we have very fine, fast oscillating structures that appear. And also we can plot at the same time in the discharge chamber the different regions of the CMA diagram. And we see that actually these structures, they perfectly match with regions of the CMA diagram that allow resonance cones. So this leads to the first question we want to answer is about the nature of these structures. We want to know if they are a physical phenomenon or just a numerical spurious solution. So to tackle this problem, we want to develop an analytical benchmark that is inspired from the classical Fresnel problem that we saw at the university in the first years or at the high school, I don't know. That basically is when you have an incident wave that comes to the interface between two homogeneous media. But our case is a bit more complicated because we study the vacuum plasma interface. So we have the challenge of the anisotropic property of plasma here. So what we did is that we developed especially an analytical solution to this problem that we can see here. So I plotted the results for different regions, and you can see here that even in regions, for example, 7 and 8, that are regions with resonance cones, you don't see the structures that we saw before. So it means that if they don't appear in the analytical solution, they are a purely numerical problem. So this leads to the second question, is how to mitigate them. To do this, we run numerical simulations on the same configuration as the analytical case, on the Fresnel problem. Here in region 1, so it's the safe case for first and second order triangles. And what we see is basically, for order 2 at least, we have a good agreement between the analytical and the numerical solutions, which validates globally the generalized Fresnel problem configuration. This whole framework is validated by this. And then we go to the region 8. So here for 2 main cases. So the first one without collisions that we see here, in which we still have the spurious modes propagating. And another one where we add collisionality. So this collisionality is defined simply as a fraction of the wave frequency. And we can see that adding this collisionality smoothens the solution. It removes the spurious modes. So finally, we want to tackle, to understand how accurate this manipulation is, because we're adding collisionality from a bit nowhere. So we want to understand how to select it, so that at the same time we remove the numerical artifacts that we saw, but that the solution stays still physically accurate. So we were looking for kind of a sweet spot here. So to study this, we ran an error convergence where we plot the error with the analytical solution compared to the damping. So here it's region 1, so you have a threshold above which the error explodes because you put too much damping. But it's normal because it's a safe region. And if you go to region 8, here you see something more interesting, is that the error decreases with the damping. And you have the formation of this valley region, which is the sweet spot we were looking for. And we can see that there's kind of actually an optimal collisionality we're looking for. Another critical effect of this, and that I want to highlight, is that this optimal collisionality, it changes with the mesh size. So if you refine the mesh, for example, to 30K elements, this optimal collisionality will move to the left on the plot. And also with 100K elements, this will shift more. So an idea that we can have from this is to implement a new numerical scheme in which we try to fit roughly this relation between these optimal collisionalities and the mesh size. So this is a more usual convergence analysis that we run, where we plot the error against the number of elements. And you see that if you use the constant collisionality, you will quickly reach a plateau phase. And it's basically useless to refine the mesh further. If you use the new numerical scheme with the adaptive collisionality, this is what you have. So I have a much clearer convergence and much lower error. Back to the ECRT simulation. So this is what I showed before. And this is the new results with collisionality. So we remove the spurious solutions. And we basically resolve correctly the fields. So now I just want to do a quick reminder about why do we do this, because maybe you got lost in all these explanations. So we're still looking for the power deposition map. That is the important thing we want to compute. So for this, we need the fields. So we resolve the fields, and now we can compute the power absorption. So here it's the previous one in the collisionless case. So again, with a lot of fine structures. And with the collisions, it looks like this, where you have a much smoother power density map and more concentration around the ECR line, which is what you can expect. A very last comment I wanted to do to conclude is that there are different ways that you can include the collisionality into the model. I tested a few, and the first evidence I have so far is that it shows that this choice of collisionality doesn't impact much the power absorption, as long as you keep the same order of magnitude, of course. But how to implement it in the map is not that important. Some achievements, and mostly future achievements, because, well, I started not that long ago. And just a quick word about the future work. So I'm developing a 3D version of the wave codes so that we can account for asymmetries in EPTs, so the asymmetry of the plasma or of the trusted geometry. And the goal is to compare this 3D code with the current 2D one that we have, and to then, if possible, explore some asymmetric configurations. This project was funded by the ERC grant Zarathustra, and also I wanted to give a special thanks to Marco for the steady state plasma density maps that he provided for my web simulations in this work. Thank you very much for your attention, and if you have any questions.